Hello, my name's Josh, and that's Max, and this is our final project for Math 40, and we did it on fractal image compression. So the background and the paper that we chose for this final project is fractal image compression by Yuval Fisher, and the core question of that paper was how you can better compress images to take up less space. And the main idea is that fractal compression actually stores the transformations rather than the image itself, which normal compression does, and how it just reconstructs the image using affine transformations. And so how it uses this transformations is it takes domain block, which is just a part of the image, a small part of the image, and it transforms it using the equation, the form of the equation on the top right, and it just scales it, flips it, stretches it, and does all sorts of things to try to fit it within the target block. And it takes these and it iterates through the target block, and it just tries to fit that target block, and then the image itself is created with a bunch of target blocks. And over time, it'll look more and more like the original image. And here are just some important keywords as well. So the idea of self-similarity is that you can use repeated parts of the same image to recreate the actual image itself. And the reason that is because in more natural photos, you can actually see that there's a lot of patterns, and you see her hat, that part on the far right, and then her shoulder is all kind of similar, and you can just use transformations to fit the target block using the domain blocks. And so we were interested in the scalability of the fractal compressions because it doesn't actually store the image itself and just transformations instead of instructions per se. You can actually stretch it, and you can actually make it larger and larger with no loss of detail at all. And it actually can be sharper. And so what we got out of it was that we wanted to explore how you can like stretch images using fractal compression and also decompress it and make it smaller. And the kind of application for this is that, okay, you can make images larger and sharper without losing anything.
All right. So we initially found our code on GitHub, which implemented a simple fractal image compression algorithm, not using all potential affine transformations, but enough to where it worked. And we also found a blog that explained how it works so that we could learn better how to use it. And so this is the code that we changed. On the right, we have the decompress method, and what we basically changed was we added this d value in the method header, which basically multiplies both the height and the width of the image by this d factor. And it also increases the size of the target and domain blocks so that the new image, decompressed image, will match the size of the height and the width of the full image. And this basically allows the decompression to now create a new image that is much bigger and has a lot more pixels in it by a factor of d. And then on the left, we have I added a median filter, which is the two for loops, in order to try and decrease noise, because we noticed as we increased the size of the image, increased the number of pixels, there tended to be a lot more noise in the image. And I also plotted both the old image and the new image that has a lot more pixels in it, and our results. And so this is our results. On the left, we have a proof of concept, which is just decreasing the number of pixels in the image. And so as you can see, there are like 30 pixels in the height. There are 25 pixels for the width in the new image, and you can see it is a lot smaller. Really isn't very significant. But on the right, we have our more important results, which is that you can see both sides of the image were increased by 2. So on the top, it was increased by it was increased to 80 by 100. On the bottom, it was increased to 100 by 150. And I think on the top, you can see there's a decent amount of noise. The writers of the initial fractal image compression paper said that this tends to not work as well with simple images. And so we tried it with a simple image, and you can see there's a lot of like black noise. But on the bottom, there's a lot less noise and there's a lot more detail. And this is a much more detailed image, and it clearly works a lot better. So we were very happy with these results. and thank you for listening.